All right, here we go. So I am working on this OTF lab, trying to parse an open type font, open what OTF file extension. It's the open type format. Open type. What does it stand for? Anyway, open type font. Yeah, that makes sense. And it's there's a specification for it. OTF specification maintained on Microsoft Docs, and the specification is very. It looks clean, but then it's very messy, in my opinion. Well, you just need to learn how to look at it, and also there's so much information that it's hard to really get a feeling for what everything means exactly. Anyway, so the the OTF font format is basically it starts with a header. Where is that? Uh, where's that? Yes? No? I should definitely read this part. Common table formats would be good to know. Deltas or item variation store. I really need to read this at some point. Um, Alright, I can't find it. That's the problem with this. Data types. Oh, it's here. So this lets you know what these data types mean that are used commonly, and then how certain numbers are encoded, what a tag is, how version numbers are encoded, and then here it is, the offset table. This is where your font file starts. So you get a version, you get a number of tables, and then you get three more pieces of data that I don't know just yet how to use. And then the num tables signals how many of these table records follow immediately after the header. And these table records contain a table tag, which I'll explain in a minute, a checksum of that table, and then the offset and length. Offset is an offset into the OTF file, and the length is the length of the table that starts at the given offset. Now, what is the table tag? The table tag is one of these: avar, base, cbdt, etc. So I am unsure which ones are useful to me right now. I have written some code that basically for all these tables, we have a field that is populated when your OTF file actually has one of these tables included. If it's not included, then it's set to a none. If it is included, it's set to a slice corresponding to the bytes that make up the table, which is nice. So a table, all the data within a table is local to the table, I hope. I don't think tables, items in tables or offsets within tables can refer to anything outside of the data of the table. That's what I hope, because then if that's the case, my approach won't work. Anyway, let's have a look at the code. Lib. So here's some utility functions that allows me to consume from the start of a slice either a single item or a slice of items, which I will show you where it's used. That will make it a lot clearer. Then we define our own error type for the parsing. Then this is a tag. It's essentially 4 bytes that can also be interpreted as a big endian integer, unsigned integer, or an integer of 2 parts. I don't know exactly. But if it's a tag, then each of those bytes should be in the ASCII range of characters from 32 to whatever 70 is in decimal. And then what else do we have? All right, so this is the table, the offset table that I just told you about. It's defined as all right, let's make this clear. So what is a U32BE? It's a U32 in big endian. So it's a new type around 4 bytes in this case. I can show you. No. Yeah, it's sort of hard to see with the macro, but it's essentially, it's like an array of a number of bytes specified here. And then it can be converted into a native endian integer of a given size through these into functions, and the into functions are defined in the standard library. They are 2 big endian and 2 little endian bytes, and etc. So that's nice. If we by defining our let's see, our tables this way, we can just cast a bunch of bytes to one of these tables, and we hope that the alignment works out. But yeah, so that's what it is. So we have the important field here is the number of tables, and then I implement this unsafe trait to signal the utility trait above that this type can be cast from a slice of bytes. All right. And then here's the table record. Contains a tag, the checksum, the offset, and the length. So that's cool. We define some constants for our tags. And then here we have a table struct, which has all of the possible tables that are defined in the spec. And then here's how we parse it. We create one of those tables, and we start consuming a raw offset table from the start of the byte slice. If that doesn't work out, we error. Then we take the table count by converting from big endian into native endian, and then we consume that many table records from the byte slice. And then we can iterate over the table record slice. And for each record, we check if the tag matches one of the tags that we have defined previously, and return a pointer to the correct field. Yep, that's how it works. I was just thinking that I could also do this by defining indices as constants and then having all the tables be an array, but it's essentially the same thing, and this is more convenient, more ergonomic. Problem is we can't really store any tables that we haven't defined, so custom tables, but right now we error if that happens. If we encounter a tag that we don't know, we just error. And the more lenient approach would be to simply ignore them or print a warning. And then with the pointer we got, we compute the bytes slice and set the field to be equal to this. If that makes sense. It's not very well explained, but I bet you know what's going on. So there we go. That's how the table is parsed. Can I run the code? I can run the code. We can. If we print the root meta, I will also print all of the byte slices and take forever. You just have to trust me that it works. It works, I think. It has worked. Should still work. So what's next? Well, the goal here is to get information from this file so that we can do our own glyph rendering. So we need to figure out, well, the first thing we want to figure out is the strokes that make up each glyphs, and so we also need to map from Unicode probably characters to glyphs. And I don't want to worry about hinting or kerning or all those things, or like graphemes. Just want to get a basic thing going. The problem is I have no idea which tables contain that information and how to read them. So that's where we're going to have to do some research. So I have some intuition as to which table could possibly contain the data. And that is the glyph. This one, the glyph table. What I was thinking about just now is that it would be useful to print some information from, like print which tables were found. But I guess it doesn't really matter. We're just gonna use the tables that we want to and then panic if they're not present. We don't really need to see what is available, but it would be nice. We could add like a print line here to hack it in real fast. Maybe like this. Can you do that? That would be nice. Panic so that it will print the tests. Print it nicely. Let's go. Alright, there we go. So these are the table records. Tag, base, checksums, big endian, big endian, big endian. Yeah, this is not very nice. We ideally want to convert these into, which must mean that we need to implement our own debug thing for raw table record. That's more work than I would like to put in. I don't see a reason to ever want to print that for consumers of our library, so we're not going to. Let's see, remove that, remove that. So the glyph table, let's have a look. Here we go, glyph data. Nice, we found the right table. This table contains information that describes glyphs in a font. Information regarding rasterize or rasterize, okay? Table organization. The glyph table is comprised of a list of glyph data blocks, each of which provides the description for a single glyph. Glyphs are referenced by identifiers, glyph IDs, which are sequential integers beginning at 0. Total number of glyphs specified in the map X table. All right, let's have a look at the max P table. This table establishes the memory requirements for this font. Fonts with CFF data must use blah blah blah. Fonts with true type outlines, similar data is required. Alright, version. So there's multiple versions of this max P maximum profile table. So what we're gonna do, we parse the tables. Max P table. We're gonna paste the documentation there. Have to get this. Ooh, I'm gonna have a fish stew tonight. Gonna have to do groceries in a bit. We're gonna try to figure out this, what is it called? Maximum profile table, how to read that. Profile. All right. Oh, that's nice. Looks like it's just a pretty simple thing. Glad that's the case. So we're gonna raw max p table. Okay, what are we gonna do? What are we going to do? Okay, we can't, I was thinking this, union, and then have a 0.5 and a 1.0 version of it, right? But then when we try to read it, we need to know what the version number is to determine how long that struct is. So this is what we're going to do instead. Strict raw mac. Well, we're not going to create a struct for the version number. We're just going to do this. So 0.5 has a unsigned 16-bit integer with the number of glyphs in the font. So what we're going to do is have num glyphs is a U16 big endian strict raw max p, and the 1.0 version has the following. Ideally, we would put this here, that there, delete that window, and yeah. Also has num glyphs. Max points. Max contours. Max composite lines. Max tours. Max zones. Max twilight lines. Max storage. I have no idea what all of these are. Max function defs. Max instruction defs. Max stack elements. Max size of instructions. Max component elements. Whoop. Why is this wrong? Oh. To n, forward n, forward n, n. And there were many n's in that thing. Max component depth. It's also that. That's the last one. So this is our 1.0 version. and save impl from raw bytes for no. Just do that. I need to figure out how to do that faster. And that one, all right, there we go. So now we want to parse that thing. Max P table is actually an enum of the P no that 5 or raw max P that. If it's neither of those, we panic. The data is invalid. We don't know this max P table. So we can implement max P table parse from bytes. Get that. Self or error. So first we do this. We can, what's a fixed? I deleted all those. I had all of the types with comments. I'm really sad that I deleted them now. Here we go. Should be here. Fixed. 32-bit signed fixed point number. So what if we do this? Fixed 16.16 big endian. Sick. I can make that transparent. Make it oh, we can make a tuple. We can make a I16BE and a U16BE. We made it of a tuple. Is this how I want to do it? No. We do this then. And then implement and save from raw bytes. And make the fields public because why not? For F16.16 big endian. I think this is what I want to do. Wow, that took me a long time. Alright. So what I'm going to do is bytes.consume single. Okay. Or invalid max p version. No, this is failing to consume enough memory. This is an unexpected end of input. This is how we want to do it. We want to read that version. So f's 0.16 big endian consume single. We kind of want to read it by value, right? Huh, I don't think my abstraction is working well. We should have a consume by reference, and then a consume by value. I don't think it makes sense to create a reference to something that is probably smaller than our type, but probably gets optimized out, but probably I don't want to have to worry about that. So this is the version field. Then we do match version. If the version matches F16, P16, big endian, oh, I could use the endianness trait. This is getting confusing. But I don't think. All right. 0.5. 0 dot into 5 dot into. Is this how it works? I don't know. Do the one thing. What's the problem here? Version 0.5. Wait, I can't do that? The into functions aren't const functions. This should not be possible. Right. 0.5. Version 1.0. Then we do a max p table. I like this more. Oh, do we want to read my reference or no? I don't know. What? Yeah, we do. We do it like this. This is awful. Oh, that's too much. Alright. bytes that consume single, okay, or error in the expected end of input. One point oh. And if we don't know what's happening, then we say error ok, and then error, sir, unknown version, max p. I don't know. God, constant uppercase. That stuff is so annoying. I think this is good enough. Version. Oh. Just do it like that. Nice. Go to the definition of that thing and known max p version. That's what you get. Derive, debug, copy, clone, ec, partial ec. There we go. Derive all the things. So now our code should kind of be close to working. Cannot find, oh, it's a parse error. Missing lifetime specifier, yep. So we use the lifetime of A to get this stuff. We can dereference the reference and then not have this lifetime. But I'm gonna try it with the lifetime, see how bad it gets. Yes, exactly. It's not a const function. That's what I said. Are the rest in 2b bytes? Is that a const function? No. Why not? Why not? Is that a public? And then 2 bytes is not a... Wait, where are we? Right, so... What the what? They are both const functions, but then the byte things aren't. We have to do it ourselves. So 0, we know that's fine. To any bytes. To BE to any bytes. We could implement our own trait. Wait, what? You do use 16 BE wrapping this. Oh, it's not visible, huh? I don't want a G tag. Alright, let's have a look at these. Just gonna create an implementation that's a const function. TE new from pub const function new takes n from ni from native Indian and we just do TE all that to big Indian. Oh, we need to know what this is. Well, to BE. Well, let's do it like that. Dot to any bytes. Cool. Why am I defining my own integer types? It sucks. Why aren't they in the standard library? There's the conversion functions, but there's no new types for them. And the new types are nice. Just allows me to not to capture what kind it is in the type of an object. Which I think makes sense, because why would we want to save on computation time? So if we're going to read a file and it contains 5 megabytes of data, and we only need to read 1 megabyte of that 5 megabytes that we actually use, and we're gonna swap all of the bytes in the file, that seems wasteful to me. So I would rather not do that. So we have self.0. Those are bytes from bytes. How does this work? I might want to change the insides of this thing to not be bytes, but the actual integer type. No, 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 no. From BE bytes. What do they do here? Self from BE, self from any bytes. From BE. From any bytes. This seems reasonable. Wait, this is a const function. But to any bytes is not. What? Wait, it is a const function. Why doesn't it say const unstable features const in conversion? Okay. Let's look up the history on that. August 2018. Ugh. Do we really want to know? I just want to do the thing. Alright. It's A. And that to any bytes. Is this right? Yeah, this is right. And then, yep, this is what we should do. From should just simply call TE from NE, and that should just call to native endian. There we go. Inline these. And then back. A16 VE from NE. No, this is an I16. U16 big endian from native endian 5. This is what I want to see. Replace the 0 with a 1. Replace the 5 with a 0. OK. Compile. We add this feature. I bet these are gonna stabilize pretty soon because, well, this seems an extremely simple, extremely trivial thing to have, and it's never gonna change, so I don't mind. Cannot be bytes mutable is not class. Yep, we need to do that because we are changing the slice as we consume things, obviously. Cannot return value referencing. That's ugly. We need to copy that thing. Why? Wait. We consume single. Clone. Copy. Why can't we just create a copy of the slice at that point? Right? That's what we want to do. I'm confused. We have a slice that's mutable. We take something from the start. I should probably write it in the way that first, like slice dot take first, split first, or something. I need an abstraction to make this nice. But what can we do now? So what I'm trying to do is put that slice in there, but I'm mutating it. How do you copy a slice? Rest copy slice. How to clone from slice? What? No. I want to clone. I don't want to clone the contents. I just want to copy the slice itself. What if we do that? Wait, we return a reference. Alright, let's take a look at the error message again. So the slice is owned. Huh? What? Uh-oh. I don't want to do this. Bytes is borrowed here. But the lifetime A should be the lifetime of this byte slice, not of the bytes itself. So no, don't G tags. So the lifetime is the lifetime of the object itself. Ah, that's what I want to do. Okay. We do this. Yeah. There's the problem. There is your problem. Oh my lord. This is confusing as shit. This is how we do it. So the lifetime of the object that we return should not have the lifetime of the slice, but of the data that the slice is pointing to. And this is how we implement that. So, oh, does it compile? Nani? Make it public. It compiles. All right, let's try to parse the table. See what happens. Let max p equals root meta dot max p bytes max p table parse and wrap. Yeah. Should make that an error, but that's a lot of work. I just want it to go. There we go. Unknown max p version. Panicked. Left, right, left, one. So the version that we got U16. Wait, are they both signed? Oh, we need to look at how this stupid fixed thing is defined. Fixed 32 signed fixed point number. So this is what we got. It's 0, 0. Uh, 80. Wait, the actual value is 80? How does that work? Is it 80 or is it that's hex? How's the byte printed? I think those are decimal values. But then 80 calculator 80 in decimal is 50. Oh, is that how it is, huh? Is that how you did it? Okay. Yeah, that's this. It's not actually the value 5. Nope. No difference represented or non-zero fractional part in fixed numbers. What do you mean? I don't know. Confusing. Anyway, this is not correct. This should just be... Well, that's strange. We should do that. We want to do from big endian bytes. Now stuff's getting confusing. From bytes. This is what I want to be able to do. And that's what we're going to implement. Does this work? Today it does. Bytes. Value is B. Self. T. Val. There we go. Bytes. T. Yeah, whatever. I don't think this is there's too many possible ways to convert. It would be good to think about where to put them, those conversion functions. Like that. Oh yes, and now we want to know the version. Max P, Tonic. I like writing the sentences. There we go. Unreachable expression. That makes sense. Numglyphs is a big endian U16. Should really change the debug to show hexadecimal. Big endian. Or just make them print. Yeah, I think hexadecimal would be nice. Well. So it's 6 times 16 plus 49. How much is that? Six times 16 plus 49. 221 glyphs. No, 145 glyphs. Ooh, is that right? What we can do is implement numglyphs. Numglyphs. Because both of the tables have that field. reference to self. It is a U16 big endian. Then we do match self. If we have a reference to max p table 05, it's not a value, it's a reference, but I can't write ref because ref's a keyword. We can return dot. Do that. So this should compile down into simply a load, a single load, right? Because these are on the same, they're the first field in both structs, so that should be optimized. What we can do now is just print I actually kind of want to include the version. Whatever. No, I should not. Well, yeah. Instead of going for an error, we can just have a max p table that's just the version. Yeah, and then have the version field and all the things. That's probably a nicer way of doing it. Oh, but then we can use the union. So we have struct max p table, and then we have like the extensions. Numglyphs isn't all of the. Yeah. Then we should limit the API. So if we define the table as a union, we can provide accessors to all the fields. But I'd rather not. We don't need to do it that way. That's a lot more work, I think, for not much benefit. So we're not going to do that. What we are going to do is call numglyph and then do a 16 from. Print it as a U16. Made a spelling error. What do we print? 1585. What can we fit in 1 byte? It's 8 bits to the power of 8. 1585. Yeah. I was thinking about like the wrong thing. Like 16 is hexadecimal. It's the number of possible values from 0 to f. And there's 2 of those in a single byte, so 16 times 62 is 65. It's It's getting late, getting more stupid. Right, so the font file I have here has a 0.5 version and only specifies the number of glyphs. And now what's the next thing? Can close that. Alright, max P, we got that glyph. Let's continue. The glyph table does not include over table records, paying offsets to glyph data blocks. Rather, the lookout table provides an array of offsets. Which provide a location. Alright, so let's have a look at the lookout table. Index to location. In order to compute the length of the last glyph, there's an extra entry after the last valid index. By definition, index 0 points to the missing character, which is the character that appears if a character is not found. The missing character is commonly represented by a blank box or space. If the font does not contain an outline for the missing character, then the first and second offset should have the same value. That didn't connect. The font does not contain the same value. Without an outline, such as space. If the glyph has no outline, then loca n is loca n dot plus 1. In the particular case of last glyphs, because the length of the glyph data. Glyph table. Alright. That makes sense. Offsets must be in ascending order. Then most routines will look at the max P table to determine the number of glyphs in the font. The value in the loca table must agree. There are two versions of this table, a short and a long version. This version is specified in the index to lock format entry in the head table. Oh, the version of this table is in another table. Isn't that great, guys? So in order to parse the loca, we must parse the head. Font header table. It seems a fairly simple... yeah, it's a fairly simple table. What does bit 0 mean? Is that a least significant bit or the most significant bit? Probably least. Flags. Alright, let's do that. So now we got the max P table. We want to look at the head table. So, and head is, oh, it's only one version, it seems. Nope. Global information about the font. Oh yes, so this, the font version. Should be set to 1, should be set to 0. We don't care what the version is. Head table. Struct. Raw head table, actually. Then major version. I don't like the way this is. 16. Big endian minor version is endian. Font revision is a F16.60 big endian. check some adjustment. U32 big endian. I don't care about it. Magic Mike. U32 big endian. Flags. U60 big endian. To do use bit field flags create to create a flag struct. Can it do big endian? No, what we should do is we have the bits and we convert from native endian to big endian. Yeah. Smart. Very smart. Flags, 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 flags. Then we have units per M. U16 big endian. Created is a long date time. Long date time. Modified long date time. X min U16 big endian X max 16 big endian I X min I min X max I max max style so another to do flag lowest recommended ppem font direction hint. Oh, nice. Deprecated. What else? There we go. Index to lock format. That's what we need to know. I16 endian glip data format I16 alright, we have a raw thingamajig. We have to define that stupid thing. A long date time is a 64-bit integer signed. Is a 64-bit big endian integer. Alright, and there's not really any magic to parsing that thing. So what we do is we mark unsafe impl from raw bytes for raw head table. Is it rep C? What's the name? Font header table. Font header. We can do this. Haha. Cool. We do let head is raw head table is root meta mac head bytes wrap dot consume single or okay, or we want to do and expect and parse error unexpected end of input. What's the problem here? Oh, should be a reference unreachable, and we can print head. What does it look like? Major version, minor version, font revision. Right, I'm going to implement debug for these and print them in native engine. Yep, I think that makes sense. Impl standard format debug for this function format how does this work? We have self and we have a mutable standard format formatter. We result as standard result. Is this the function signature? What should the return type be? Ah, okay. Rest formatter. How do we get a nice debug struct? Oh, stringify t. Yeah. Dot field. Tuple. Field self dot 0. We do to any. There's no to any. Yeah, there is. Finish. Oh. We have to remove the debug trait. How do we look? How are we looking? That's better. Why aren't those in line? I want it to be in line. Because this sucks. Alright. Right. F. Cat. String fi. te. With. How do we look? That's what we want to see. Yeah, it's not the best. It's not the worst. Alright, it's better than what we had. Good enough. It's just debugging. Max P. So we have a max P table. Version 0.5. Number of glyphs is 1585. Then we have a raw head table. We have the major version set to 1, minor to 0. Font revision is a fixed point 1.6555. I don't know what that comes down to, but whatever. It's like major minor probably. It's just, that's what it is. Interesting. If that really corresponds to anything, or if it's not properly set by the source code variable people. There's a checksum, there's a magic number. Flags 1 and bits 1 and or 0 and 1 are set. What does that mean? Baseline for font at y is 0, and then bit 1 left side bearing point at x is 0. LSP. Left side bearing point. What is the left side bearing? I don't know. We'll have to find that out at some point probably. Units per M. 1,000. Ah. Okay. That's good to know. Some timestamps. Then x minus x min, I min, x max, y max. So divide this by 1,000. Or range? Why is this so large? Should this be a signed thing? It's probably to's complement. Yep. Good. Found a bug or a misdeclaration. These are obviously all integers. Alright, yeah, that makes more sense. That's way better. Then we have a max style, which also flags lowest recommended ppm. 3? Oh yeah, deprecated set to 2. It's 3! It's not even a thing. Should be an int. No, it shouldn't. Oh no, it's a font direction hint. That's oops. Smallest readable size in pixels. 3. Wait, it's readable at 3 pixels. Wait, pixels per m. 3 pixels per m. 3 pixels per character. That's still readable, really. It's unlikely. Glyph data format is 0, and that's what we were interested in. No, we weren't. Nope. This is what we have short offsets, not the long ones. So offset 16. Good. So we can commit this stuff. What's going on? Emacs, no. Yeah, save it. Alright, what did we do? Oh, what did we do? We added type. We added fixed point. We changed the signature. And we just commit everything. Right. Add the... Did we parse? No, not loci. We parsed head and max p. Parse max p and head tables. Fixed the byte slice trait signature. Should return at reference with the lifetime. To bytes passed to the function, not the lifetime of the slice itself. And then we added the profile, we added the thing, and we did the debug. Added a conversion. Add const constructors for big, little, endian types. Your types that improved for and integer it's better. That's what we did. Push it. And I'm gonna go do groceries now. Thank you for watching. I hope you've learned something. And I hope that was remotely interesting.